Unit 11, Intermolecular Forces and Liquids and Solids. So if we think about carbon, carbon has three main crystalline forms. Diamond, which has a tetrahedral shape, is the hardest natural occurring substance. Because of its tetrahedral shape, it's a poor conductor, and it's transparent in the pure form. Graphite, however, carbon is arranged in a trigonal planar, so it's soft, it's an excellent conductor, it's dull gray color. Now a buckyball is when the carbon atoms are in a cage shape that are joined together to form nanotubes. Now this cage shape kind of is reminiscent of like a soccer ball type shape. It conducts electricity and is extremely strong. So it's actually used in everything from tennis rackets to human tissue engineering. Nanotechnology using these nanotubes is a high expanding or high interest form of chemistry. So the difference between these forms of carbon is how the carbon atoms are joined together. So the bonds linking one particle to another helps us understand what liquids and solids are. When is something a liquid, when is something a solid? That's determined by the intermolecular bonds. So the kinetic molecular theory of liquids and solids. Let's review gases first off. Gases, we remember, are in constant range of motion. The molecules are so far apart from each other that they don't interact. So the intermolecular forces don't play a role in gases. Because of that, there's a large amount of space, means it's compressible. Because they don't have strong forces, gases can expand and fill any volume, and because they can fill any volume and have large amounts of space in between them, they have low densities. So the main difference between the phases then is simply the space between the molecules. The closer the molecules are, the more the intermolecular forces play a role in those properties. So this table, 11.1, shows the characteristics of gases, liquids, and solids. Liquids are closer together than gases are, with very little space in between. They're held together by either one or more types of attractive forces. So because the attractive forces are now playing a role, it has a definite volume. It can still take the shape of its container though. Liquids have a higher density than gases. Liquids are only slightly compressible, so because there's still a little bit of space in between, we can compress them. And they still slide past one another freely. Solids, however, are held rigidly in position with virtually no freedom of motion. We say they just vibrate in place. They are arranged in regular configurations in 3 dimensions and have even less space between them. So they have a definite volume because they're in a fixed, rigid state, and they have a fixed shape. They have typically a higher density than liquids and gases. The one exception there is your water. Water solid is actually less dense than its liquid. Solids also are virtually incompressible because the molecules are so tightly packed. And again, the molecules just sit and vibrate in a fixed position. So they are moving, but they're in a fixed position. So 2 states of matter can coexist, for example, ice and water. Or if we look at this picture, we have solid and air. The different states in the system are referred to as phases. So a phase is a homogeneous part of a system in contact with other parts of the system, but separated by a well-defined boundary. And we can usually see that. So we can see our ice cube floating in our liquid. There's a defined boundary there of the ice cube. Intermolecular forces are attractive forces between molecules. So we're not talking about the bond, we're talking about in between molecules. We're not talking about H and O in water, we're talking about H2O compared to H2O. Intermolecular forces are responsible for non-ideal behavior of gases. The more or the stronger the intermolecular force of a gas, the less ideal it becomes. Intermolecular forces exert even more influence on condensed phases like solids and liquids. So as the temperature drops, the average kinetic energy decreases. Eventually, the molecules will no longer have enough energy to break away from the attraction of the neighboring molecules. So they no longer have enough energy to break away or break the intermolecular forces. So then the molecules undergo a phase change. So we're not breaking the bonds and we're not forming bonds, but we're forming attractions. Intramolecular forces are what holds the atoms together in the molecule. That's what we talked about in Unit 9 and 10. They stabilize individual molecules, but the intermolecular forces are responsible for the bulk of the properties. So melting point and boiling point, for example, are explained using intermolecular forces, not intra. Intermolecular forces are much weaker than intramolecular forces. It usually requires less energy to cause a phase change than to actually break the bond. Boiling points often reflect the strength of the intermolecular force operating among the molecules. So enough energy has to be applied to overcome the intermolecular force before a phase change can occur. So the types of intermolecular force. You have dipole-dipole forces, which are attractive forces between polar molecules. Between molecules that possess dipole moments, the dipole moment comes from electrostatic forces and is understood in terms of Coulomb's law. The larger the dipole moment, the greater the force. In liquids, they tend to align in such a way that maximizes the attractive interactions. Here we have a picture of a solid, so it's very patterned, very ordered. Ion-Dipole Forces is the attraction of an ion to a polar molecule. The strength depends on the size and the charge of the ion, Coulomb's law. The magnitude of the dipole moment and the size of the molecule. So the cation interacts more strongly than an anion because the cation is smaller than the anion. Hydration, back from chapter 4, is an example of this. So if we look at our two pictures, we have a sodium ion compared to magnesium plus 2. There's a stronger attraction here because the molecule is smaller and has a greater charge. Dispersion forces. An induced dipole is a separation of positive and negative charges in the atom, or the nonpolar molecule. It's due to the proximity of an ion or a polar molecule. So in picture A, we have a neutral atom, let's say helium. When helium comes near a cation, we have this induced dipole, this positive and negative end. So that would be an ion-induced dipole interaction. If it was another polar molecule that it was coming in contact with, we'd still have that induced dipole because of the polarity on the polar molecule. So that would be a dipole-induced dipole interaction. Dipole moments not only depend on the charge or strength, but also on the polarizability of the atom or molecule. Polarizability is the ease at which the electron distribution in the atom or molecule can be distorted. So the larger the number of electrons, the more diffuse the electron cloud. So diffused electron cloud just means a larger electron cloud. The greater the polarizability. Instantaneous dipole is a dipole lasting just for a tiny fraction of a second. So that's what happens in a nonpolar molecule. In a nonpolar molecule, your electrons might be over here causing a dipole, and then in the next split second, they're on the other side causing the opposite dipole. Dispersion forces are the attraction forces that arise from the result of this temporary dipole. So here you can see a snapshot of a nonpolar molecule and how the instantaneous dipole can change. Dispersion forces or London dispersion forces or London forces usually increase with molar mass because the molecules are larger. And when the molar mass is larger, the atoms tend to have more electrons, which means the dispersion forces increase in strength with more electrons. So the larger the molar mass usually means the bigger atom, so the electron distribution is easily disturbed because they're held less tightly from the nucleus. They're shielded more. So if we look at the melting points of some nonpolar compounds, you can see that the melting point is increasing as our size is increasing. So name the type of intermolecular force that exists between molecules or basic units in each of the following species. Well, LIF is ionic, so it would have ionic forces or electrostatic forces, and it also has dispersion. Everything has dispersion forces. CH4, if we draw the Lewis structure, is a nonpolar molecule, so it just has dispersion forces. SO2, if we draw the Lewis structure, would be a polar molecule, so it has dispersion forces and dipole-dipole forces because it's polar. Hydrogen bonding is a special type of dipole-dipole interaction between hydrogen atom in a polar bond and the electronegative atom, nitrogen, oxygen, or fluorine, NOF. The average strength of the hydrogen bond is quite large, so they have a powerful effect on the structures and the properties of the compounds. So these red dots in between here represent the hydrogen bond. So it's the hydrogen from one molecule being attracted to the lone pairs on another molecule. The strength of the hydrogen bond is determined by the Coulombic interaction between the lone pair of electrons on the electronegative atom and the hydrogen nucleus on another molecule. While fluorine is the most electronegative, we would tend to think that fluorine would be stronger hydrogen bonding. But actually, oxygen is stronger than fluorine. Water has a stronger force than HF because HF only forms one bond, where if we think about that picture of water, water actually has the ability to form two, and then its hydrogens could form another two hydrogen bonding. So it's a much stronger force of attraction there.